sorry. The review is on Blackboard. Um, well, if you're in my class, yes, it's on Blackboard. But what I did was I had to reformulate it into a PowerPoint slide.
Professor, can I ask you a question?
Yeah, sure, Kanisha.
Is there a sheet that we could use to follow along with you, or are we just going based off on your screen?
You're gonna go based off of my screen. So if you want, the questions are on Blackboard. On your end, you can follow along, do the problems with us on your end, and just keep in mind that you might need your z table. You will need your z table.
So is the final created by the math department?
Um, well, it depends on what who's your instructor for pre-calculus. But no, sorry, not pre-calculus. I'm sorry, for statistics. But
Uh, Conrad?
he creates the final.
Oh, okay, great. Awesome.
Yep. Yeah, so the 132 instructors are responsible for creating the final exam. All right, it's 10:15. I'm going to share my screen off my iPad. So the screen of the whiteboard will be closed. And again, I'm going to pull up from my iPad the sample final. Give me 1 second. All right, so there you go. You guys should be able to see my screen off my iPad. I'm just gonna reopen the chat window. No, Edwin's actually in my class. Lauren, sorry, I'm just answering some of the things in the chat. So I think you should, if you are in Professor Lack's class, then I think you probably have to email him if you can't find the exam materials. I think you should. You should be able to. I think it's probably in that very last module, or he probably created a separate tab on Blackboard. It's kind of hard for me to know because I can't see your screen. Maybe Raphael could help you. Maybe. All right, so I want to begin. I want to go over the solutions to the sample final. Please feel free to participate and ask questions as I go through our sample final. Just remember, by the way, that on Tuesday at 6 p.m., I will go over a second version that the Math Student Success Center, MS3, created for you guys. So I will go over that on Tuesday at 6 p.m. Today, we're just going over the departmental sample final. Okay, so here's problem number 1. It states, in a survey, 1,465 internet users chose to respond to this question posted on a newspaper's electronic edition. Is news online as satisfying as print and TV news? 52% of the respondents said yes. So we have to answer parts A through D based on what's given there, based on this situation. So part A states, determine whether the study is an experimental or an observational. So what do you think? Is this study an experiment or observation?
I think it's experimental.
Why do you say experimental, Edwin?
Well, it says that it's new online as satisfied as print and TV news. So basically, that was a question, and 52% say yes. So I think it was experimental.
Well, if it's an experiment, then your participants of your study must be given some sort of treatment or medicine, right? Just like what Sheldon's pointing out in the chat.
Got it.
So it cannot be an experiment because of that reason. None of the respondents were given any treatment. There was no medication. There was no attempt to modify the individuals. So it has to be an observational study. Okay, all surveys are observational, right? So note, I'll write it out here. So for part A, this is an observational study. Because the researcher does not modify, right? So when I say modify, I'm implying does not give any medicine or treatment. Does not modify the individuals in the study. All right, so another note is that all surveys, whether it's a online survey, opinion polls, telephone polls, newspaper surveys, all surveys are observational. Okay. The researcher is not attempting to modify any of the individuals of the study. And that is your solution. Okay? Excuse me. All right, so that's part A. Part B states to identify the sample and the population. So, when you're looking at the sample and the population, just remember that the population is everyone of interest, right? Everyone of interest, whereas a sample is a subset of that population, okay? So we got to identify both the sample and the population here. So you could begin with either or, it's just the way that you word it that you have to be careful with. So what do you think will be our, what would you think will be our sample? Oh, Malik got it for us in the chat. So the population here is going to be all internet users. That's right. It's going to be all internet users. Because again, who's of interest in this study is those that uses the internet. On the other hand, the sample is the 1,465 internet users that responded to the question. Okay, so your sample is 1,465 internet users that responded to this question. The population is the all internet users. Namely, it's everyone that basically uses the newspaper's electronic edition, okay? All right, so we have our sample and our population. Now, part C asks you whether or not if the value 52% is a statistic or a parameter. So what do you guys think? Well, in this problem, it says that 52% of the respondents said yes. Well, who are the respondents here? Is it all the internet users? Or was it the 1,465 internet users?
The 1,400 that responded.
That's right, Christopher. It's the 1,465 internet users who responded to the question. We know that the 1,465 internet users is part of the sample. So therefore, the 52% must be a what? A statistic or parameter?
A parameter?
Nope. Sorry, it's a statistic. All right, 52% is a statistic because, I'll explain. I'll write a quick sentence to explain this. It's because the data, right? The data that was retrieved from the survey comes from the sample, all right? So the 52% is a statistic because the data retrieved came from the sample. It came from the sample, right? It came from those that responded to this question. And who were the people that responded? It was the people from the 1465 internet users. Okay, it would have been a parameter if it said something like 52% of internet users said yes, right? If it said 52% of internet users said yes, or 52% of all internet users said yes, then that would have been a parameter. But that's not the case here, okay? When you're looking at a population, one of the key phrases regarding the population is that it uses the word all. Okay, now we do part D. Part D states to identify a major problem with this study. So, what is a major problem regarding this statistical study?
It's optional, so there can be a bias.
That's right. In a sense, this is like convenient sampling, since the newspaper electronic edition posted, again, they post this question on their website. So for the convenience of the audience, they can respond to this question. In particular, it says that these internet users chose to respond to it. So it's voluntary. And like you were mentioning, voluntary convenient sampling can lead to biased results. Right, so part D, we can say that this is a convenient sampling. With voluntary response. Which leads to bias results. That's why when you are studying things like, for example, confidence intervals or hypotheses testing, it says that one of the basic requirements of hypotheses testing or confidence intervals is that your sample must come from a simple random sample. Simple random, okay? Anything else, such as convenient sampling, with this voluntary to respond to these questions on this website, it leads to biased results. It leads to biased results. All right, so that is problem one. That's all the solutions to parts A through D to problem one. Is there anybody that has a question?
Sorry, could you just quickly review the difference between random and simple?
No, random and simple is the same thing. They say it's a simple random sample.
Oh, I'm sorry. Then it's simple and something else.
Well, the different type of sampling methods are like convenience is one, simple random. There's other ways to do somewhat of a random sampling. There's systematic. There's another one that starts with an S. I just can't pronounce it at the moment. Stratified, I think it is. Stratified. But on the final exam, for this type of problem, when it asks you a major problem, you got to understand that the major problem here is that, again, based on the way that the problem is worded, there's going to be some sort of biased results. Here, the biasness comes from the fact that people voluntarily respond to this question. So, therefore, if they strongly oppose or if they're strongly opposed or against or strongly for something, then you're going to have that many people will respond to this question. However, if you have somebody that's somewhat in the middle, then they won't typically respond. If they're not neutral, I mean, if they're neutral, then they won't really respond to this question. Anybody else? Any other questions? You're welcome. All right, so let's continue. Let's move on. Let's look at problem number 2. Problem number 2 states that a store manager kept track of the number of newspapers sold each week over a 7-week period. The results were as follows: 81, 71, 202, 113, 269, 248, and 242. We want to find the 5-number summary for the data, and then when we're finished with the 5-number summary, determine if the data is discrete or continuous. So I have some notes for us. Again, I'm going to show you, I should have mentioned this earlier, that for all the problems that we're going to go over today, I'm going to show you how to do it by hand, meaning that I'm going to show you how to do most of the setting up the formulas and things like that we use, and then we're going to use the calculator to do some basic computation. So if I'm solving this problem by hand, the 5-number summary consists of the following, right? So it consists of the minimum value, which is the smallest. It consists of Q1, Q2, Q3, and the maximum. So when I said Q1, Q2, and Q3, those are quartiles, right? And when you think about a quarter, it's basically 25. So Q1 is the first 25, Q2 is the halfway point because that's 50, and Q3 is 75. So by definition of these words, if you want to do them by hand, Q1, Q2, and Q3, you can find them by using the median, right? Q1 is going to be specifically the median of the lower half. Q2 is the median of the upper half. No, not the upper half, I'm sorry. Q2 is the median of the entire data set. And Q3 is the median of the upper half. The maximum, again, is the largest value in your data set. So if I'm trying to solve this problem, one thing to note is that you have to put the values in order, okay? You put your values in order. So in order, we have the following values. 71 would go first, followed by 81, followed by 113, then 202, then 242, then 248, and 269. So once I have my values, my data values in order, the way that I'm going to find the 5-number summary is that I'll first find the minimum and maximum. I do that first. Then I find the median of the entire data set, which is Q2. Again, Q2 is the 50% mark. Half the data values are going to be below this value. The other half is going to be above it. Once I find the Q2 value, then I can find Q1 and Q3, okay? So, excuse me. So if I want to find Q1, sorry, not Q1, the minimum, then that would be, again, the smallest value, right? So what is the smallest value in our data set?
71.
71, and the maximum?
81. Oh no, 269.
There you go, maximum is going to be 269. All right, so we got the min and max out of the way. Now we can get Q2 out of the way. So again, if I want to find Q2, go ahead and take the median of your entire data set. So I'm going to say Q2 is equal to the median of the following numbers. Well, it has to be all the numbers. 71, 81, 113, 202, 242, 248, and 269. Now, how many data values did we have in the original data set here?
7.
We have 7 data values. Since 7 is an odd number, then the median is going to be precisely equal to what? If I have 7 data values, then the median of the entire data set is going to be equal to which value?
$202.
202. That's right, because 202 is the middle value, right? So here we get that the median is 202, or namely that's Q2, right? So what do we have so far? Well, we have 71 is the minimum. We have 202 is the Q2 value, and of course 269 was the maximum. So usually I label these things out in my data set because now when you have it labeled, it's easier to find Q1 and Q3, right? Because by the definition or the way of finding Q1, it says that you take the median of the lower half. The lower half are the values that are less than the median of the entire data set. So if the median of the entire data set is Q2, which is 202, then Q1 is equal to the median of what values? Can somebody tell me?
71,
Uh-huh.
81, and 103.
113, yes. Okay. So Q1 is equal to the median of the lower half. The values in the lower half are only going to be 71, 81, and 113. So if we work this out, what would be the median of this lower half?
81.
It would be 81. And that's it. Right? And of course you could have just plot that in real quick, that's your Q1. And now you go ahead and find Q3. So Q3 is the median of the upper half. So what values are now in the upper half?
242, 248, and 269.
There you go, 242, 248, and 269. So again, we have only 3 values here. So the median is going to be the middle value. The middle value here is 248. So this will be your Q3. And that will be it. So in if you want to write out the 5-number summary in order, we can say that the 5-number summary in order from lowest to highest, right? The 5-number summary is just going to be 71 followed by 81, 202, 248, and 269. And that's it. That would have been your 5-number summary. Now, one of the things, by the way, is that once you find the 5-number summary, you can create a visual. Do anybody remember what that visual is called?
The box and whisker plot.
Yeah, you could create a box and whisker plot. That's right. Or just in short, a box plot. Right? So visually, I mean, this wasn't being asked in the problem, but if it is, then it's good to know. So visually, we can construct a box plot. Oh, sorry, I spelled box plot wrong. So the way that the box plot works is that you have a horizontal axis, right? An axis that runs from left to right. And then you guys just got to do some scaling here. So what I'll do is, looking at our numbers, the lowest number was 71. The highest number was 269. I could have scaled this by 10s. I could possibly did 20s. I think 30s would have been a little bit more reasonable in terms of scaling. Right, so let's say that here is where we're starting at. Let's say 0. Let's say here's 30. Let's say here's 60. Here's 90. 120. 150. 180. 210. 240. I'm going to need a little bit more room. Oops. So here was 240, and let's say here's 270. All right, so the way that the box plot works is that you can plot the 5-number summary, of course. You locate where they are. So let's say that 71 is somewhere a little bit closer to 60. Again, I'm just making some approximations here. This is not done strictly by a strict scale. but let's say 71 is there. Let's say here is 81, should be a little closer to 90. All right, so far we have the 71, we have our 81. Then we plot the 202. So 202 would have been a little bit closer to 210. So that would have been, again, 202. We got 248, which is a little bit closer to 240. And then 269 should be close to 270. All right, so the way that the box plot works is that once you have the 5 numbers plotted, you can draw a box that goes from Q1 all the way to Q3. So Q3 was 248. You can draw a vertical line that goes through your second quartile, which was 202. And you can draw the little whiskers now, basically extending to your min and max values, right? It basically extends from your box to the minimum, and then the right end of your box to the maximum. Sometimes it's optional, but you could draw that. You could just draw that line that goes through it as well, if you wanted. It depends on the instructor how they want their box plot, but nonetheless, there it is. Oops, I forgot to plot the other 2 numbers. So again, it was 248, 269. So that's what the box plot looks like for problem number 2. Okay. The last thing that this question asks us was, is the data here going to be discrete or continuous? So to answer that part of the question, you just got to know what discrete and continuous means. Discrete, I'm just going to scroll down just a tad bit. Discrete means that the data set is countable, right? Data can take on specific values. On the other hand, continuous is where the data is uncountable, and we refer to this as measurements. Because if you think about measurements, you can think about scaling. And when you deal with scales, data can take on any value you want on a data set, on a given interval, right? So data takes on any value. In an interval. So, in this problem, we were looking at our data being the number of newspapers sold each week, okay? So, since I'm dealing with the numbers of newspaper that are being sold each week, do you think it's going to be discrete or continuous?
Discrete.
Discrete.
It's discrete, that's right. So, for this problem, again, the variable that we were dealing with here was the number of newspapers. The number of newspapers, the newspapers sold each week, is discrete. One of the reasons why it's discrete is because if you think about it, it makes more sense to say, for example, I sold 269 newspapers than saying I sold 269.25 newspaper or 269.5 newspaper. When you go to a deli, for example, I know you probably won't pick up a newspaper now, in terms of nowadays, with modern technology. But if you were to pick up a newspaper, the store owner will even if you were just wanting to read one little article or just take one article out of the newspaper, you got to still purchase the whole newspaper. You just can't take that one article out, or you just can't take the coupons out of a newspaper, right? You got to purchase the whole thing, right? So discrete is discrete because, again, it's countable. Another way that you can distinguish between discrete versus continuous is that when you're always talking about discrete data, it will say something of number of. That's a clue. That's a big clue. That means that you're counting the objects. Continuous, on the other hand, if it talks something about temperature or some sort of scaling, like, how many inches of snow fell in New York City in the month of December, that would be continuous. Data can take on any value in that interval. You could say that, it snowed only a cumulative of 3 inches, 3.165 inches. But again, to make sense of those numbers, of course, rounding are typically done. All right, that was problem 2. Any questions? Any questions for me? All right, we're going to move on. We're going to go on to problem number 3. So problem number 3 states, consider the scatter plot given below. Which of the following could be the value of R? Then it states, given the regression line has a slope of negative 0.128 and a y-intercept of negative 0.155, find the slope-intercept equation of the regression line, and then use the regression line in part C to predict the y value for the value of x. All right, so for part A, when you have to find the value of R, just remember that R is always between 2 values. R is always between 2 values. What are the 2 values that R is always going to be between?
Is it 0 and 1?
Not quite. 0 would be actually in the center. 1 will be on the right. So what number is on the left?
-1?
There you go. It's -1. Okay, so if we have values that are, let's say, between -1 to 0, will we have a positive correlation or positive linear correlation or negative correlation?
Negative.
They're negative, okay? So here we have negative correlations between -1 to 0. And then from 0 to 1, or anything greater than 0 would be positive correlations. All right. Now, at -1 and at +1, you have perfect correlations. Either it's going to be a perfect negative correlation, or at +1, you have a perfect positive correlation. When I say perfect, I'm implying that all the data values are going to fall in a straight line, where the line is either going to be decreasing or the line is increasing. Now, to help you break down the other stuff, you can use these values. You can say that somewhere between -1 and 0, you have these 2 values. Let's say -0.7, -0.3. And on the positive end, let's say we have the 0.3 here and 0.7 here. So in between -1 to -7, you can say that the correlation is going to be a strong negative. Similarly, between positive 0.7 to positive 1, you can say that you have a strong positive correlation. Between -7 to -3, negative 0.7 to negative 0.3, you can say that it's moderate. Anything now in between negative 0.3 to 0.3, we say it's weak. Okay, it's weak. And then, of course, the closer you are to 0, there's no correlation. So this little breakdown sort of gives you the clues which you need to help you solve part A, right? So part A says, when you look at the scatter plot below, which of the following could be the values of R? Well, we have 5 options here. What are 2 options that we can automatically get rid of? If you look at the values of R, what are 2 values that we can automatically get rid of?
The positive values?
Yeah, we could get rid of the positive values. Why can we get rid of the positive values? Because if you read your scatter plot from left to right, you can see that it is a negative correlation. Okay, so those 2 values that I crossed out, we can get rid of them because, of course, they're positives. Now we're left with 3 negative numbers. Now, since we already know that this is a negative correlation, is this correlation a weak one, moderate, or strong?
Strong?
It's a strong negative, right? So it's actually, instead of saying a negative correlation, it's a strong negative correlation. So what other values can we eliminate? I'll give you a hint. Since we said it's strong negative, then it must be between -1 to negative 0.7. That's right. You can get rid of the negative 0.309, and you can also get rid of the negative 0.679. So by process of elimination here, we found the value of R, right? Based on the scatter plot, it suggests that R is equal to negative 0.996. And you're done. That's it for part A. So I'll put a check mark on it. Now we go on to part B. So part B, it says, given the regression line has a slope and a y-intercept, find the slope-intercept equation of the regression line. So in the textbook that we use for stats, Triola mentions that the way that you write the regression line is in the following notation. And we say y hat is equal to b1 times x plus b nod. This is no different from the y equals mx plus b. Okay, so the notation here, y nod equals b1, y hat equals b1 times x plus b nod is no different from y equals mx plus b, right? Because this value b1 is your m. And we should know that m stands for what? The slope or y-intercept?
Slope.
That's your slope. And we know that b nod stands for the value of b, which is the y-intercept. Okay, so since I know what my slope and my y-intercept are, I just got to plug it into this equation. What we're going to get is y hat is equal to negative 0.128 times x plus the value of the y-intercept, which was negative 0.155. Now, you can simplify this equation just a tad bit here, right? If you look at your equation, you can simplify the plus and the minus, right? If we have a plus sign and then followed by a minus sign, then a positive and a negative, what does it make? Does it make a negative or a positive?
Negative.
Makes a negative. So the equation of the regression line should have been y hat equals negative 0.128 times x minus 0.155. All right, so that will be the solution to part B. Now that you have your regression line, you can solve part C. Part C states basically when x is equal to 0.45, find the value of y hat. So when x equals 0.45, I make a direct substitution into my equation. What we're going to get is y hat equals negative 0.128 times the value of x, which is 0.45, minus 0.155. So if you're doing this by, this is a part where you need your calculator for. You can multiply the negative 0.128 by 45, get an answer, right? So if I multiply this two numbers, we get something like negative 0.0576, and then I subtract it by the 0.155, right? So we get negative 0.0576 minus 0.155. And if I did this correctly, we get negative 0.2126. And that will be your solution. Somebody asked me in the chat, how did we get the slope and the y-intercept? You see, the slope is defined as b1, right? If you look at the way that I described it here in part B, b1 is the same thing as your slope, which is m. So that would be this value here. And the y-intercept is b naught, which is b. So it goes here. All right. Is there any questions to problem 3? To be very honest, other than maybe, possibly, you mistyped something into a calculator, I don't think any student should personally get this problem wrong. The only thing that could possibly make you lose points is if you type this equation incorrectly into your calculators. So if you're doing this in the calculator, make sure that you begin with the negative 0.128 times 0.45, get a solution, then subtract it by 0.155. And that's how we get the negative 0.2126. Any questions? All right, we're going to continue. We're going to move on to problem number 4. So problem number 4, it states that the table below describes the smoking habits of a group of 1,156 asthma sufferers. So the table is a two-way table, right? The table is split up into two variables, one being splitting it up based on gender, men or women, and the other one is based off of the person's smoking habit, whether the person is a non-smoker, occasional, regular or heavy smoker. So part A states if one of those people is randomly selected, if one person is randomly selected, find the probability that the person is a man or a heavy smoker, and then at the very end, you round to 3 decimal places as needed. I'll come back and do part B, but let's get part A out of the way. So when you read part A, that question, it's very important that you read these questions, because in part A, they give you a key word that gives you a clue on how to solve this problem. What is the key word to part A?
Or
Yes, that's right. It's the word or. Now, when you see the word or in probability, what probability rule comes to mind? Or yeah, what formula, what probability formula comes to mind when you read the word or?
The addition rule.
That's right, the addition rule. So the addition rule states that if you have the probability of A or B, right, the probability of A or B, this is equal to the probability of A happening plus the probability that B happens minus the probability that both A and B can happen simultaneously, right? We have to do the subtraction at the end if needed, whatever 2 events can happen simultaneously. This is a problem where 2 events, namely your event that the person is a man or a heavy smoker, can happen simultaneously because the table gives you the number of men that are heavy smokers, right? Or the number of heavy smokers that are men. So the way that I'm going to solve this is as follows. The person is a man. That will be my event A. My event B is the person is a heavy smoker. So I'm just going to make some substitutions into my formula. We have that we want to find the probability that the person is a man or heavy smoker. So for the heavy smoker part, I'm just going to abbreviate it as HS. So just note that HS doesn't stand for high school, stands for heavy smokers in this problem. Okay, so that's your HS. So this is going to equal to the probability that the person's a man plus the probability that the person is a heavy smoker minus the probability that the person is a man and heavy smoker. So all we got to do is just figure out what these probabilities are, okay? So what I need you to do is express each of these probabilities in fraction form. For example, if the problem was just to ask us, what is the probability that the person is a man, what would the fraction be?
601 over 1156.
That's right. In this data set, there's a total of 601 men out of 1,156, right? So you can think of the 1,156 as your grand total or your sample space. So we have 601 over 1,156. Okay, now, what is the probability that the person is a heavy smoker?
88 over 1156.
That's right. There's 88 heavy smokers in this data set out of the 1,156 minus the probability that the person is a man and heavy smoker, meaning that they both happen simultaneously. So if I chose one person at random, what is the probability that that person is, again, a man and heavy smoker?
49 over 1,156.
That's right, because the 49 is the intersection between the two variables. Right? If you look at where the men's row versus the heavy smokers column, that's when that row and column intersects. So we get 49 out of 1,156. So therefore, in the numerator, because the denominator is the same, 1,156, all you have to do is just add and subtract the top numbers, right? So you do 601 plus 88 minus 49, and then we're going to subtract that, then we're going to divide it by 1,156. So if I take 601 plus 88, you're going to get an answer. Then when you subtract it by 49, that becomes your new numerator. So what is 601 plus 88 minus 49?
640.
640. So we're going to get 640. And now if I take 640 divided by the 1,156, you're going to round your answer to 3 decimal places. So what would the final answer look like?
0.554?
Yes.
0.554?
That's right, 0.554. And that is the solution to part A. We get 0.554. All right, so when you read part A, you're applying addition rule because the key word there is that we're finding the probability of two events separated by the word or. Part B, we're going to do it almost in a similar manner. We're going to figure out what's the key word. We're going to write out a formula. And of course, I'm going to describe that formula in plain English. All right, so part B. It says if one of the people is randomly selected, find the probability that the person is a regular smoker, given that the person is a woman. So what is the key word into part B, into solving part B?
Given.
The word is given, right? So given is our keyword. And what probability rule comes to mind when you think about given?
Conditional.
Conditional probability. So there is a stricter formula to finding conditional probability inside of your textbooks. However, when we're finding conditional probability where the data is being presented in a two-way table, I do it informally, right? So observe. The notation for conditional probability looks like the following. We say probability of B or event B given that event A already occurred, right? That's what that notation means. B given B bar A means the probability of event B occurring given that event A already occurred. So the way that I figure this out is I first figure out the bottom number. Get the bottom number first. The bottom number represents the number of ways in favor of event A occurring. So a synonym to occurring is also happening. And on the top number is the number of ways A and B can happen simultaneously. Right, so we say number of ways A and B can happen simultaneously. So my recommendation is that you find the bottom number first, right? Find the bottom number first. Then find the top number secondly, right? So you find the bottom number first, and then you find your top number. So if I replace my notation with the words given in this problem, we have that the person's a regular smoker given that the person is a woman. So in this notation, we have that the person is, again, going to be a regular smoker. I'm going to abbreviate that as RS, given that the person is a woman. So what is this going to be equal to? Well, on the bottom, looking at my recommendation, you find the bottom number first, which is the number of ways of selecting a woman. So if we look at our data set here, how many women are in this data set?
555.
That's right, there's 555 women. So we have the 555 that goes on the bottom. That's the number of women in this data set. Now, out of that 555 women, how many of them are regular smokers?
86.
86. Right, so it's going to be 86 out of 555. Right, so again, the way that conditional probability works is that the bottom number is always equal to the very first event happening, and that was the number of ways of selecting a woman. So there's 555 ways of selecting a woman, and out of that 555 women, there are 86 of them that are regular smokers. So as a fraction, your probability is 86 over 555, and you round your answer to 3 decimal places. If you round your answer to 3 decimal places here, you're going to get something like 0.155. Any questions to part B? So again, if you were solving this problem, you find the bottom number first, and then you find the top number secondly. All right. Any questions? Okay, I'm going to continue on. We're going to look at problem 5. Problem 5 states a tennis player makes a successful first serve 51% of the time. Assume that each serve is independent of the others. If she serves 9 times, what is the probability that she gets at most 3 successful serves in? So when I want to solve problem number 5, what type of probability is this? Or what type of probability formula is used to solve problem 5? Not quite, Sheldon. You're on the right track. I know what you imply by those notations. 1 exclamation point, 2 exclamation point, 3 exclamation point. I understand where you're coming from, but you got to give me the name of the probability formula that I use here. Do you know it? Or if you know what the formula looks like, you can give me that as well, and then I could tell you the name.
A classical.
No, it's not a classical. Well, I mean, I do it the classical way. That is right. I don't do it the calculator way.
That's like n choose x.
Say it again, Malik.
Is that like n choose x?
That's right. You have the n choose x. What comes after the n choose x? You got to multiply it by something. What do we multiply n choose x by?
The probability.
There is a probability. I mean, we are computing a probability. We're namely computing the probability of x here.
Mhm.
So it's n choose x times. There's 2 more things that we need here. What comes after the n choose x?
The probability of success.
The probability of success. That's right, Edwin. It's p
X
raised to the x power
times Q and N minus X, I think.
That's
yes.
right. Q raised to the power of n minus x. So this, again, if you're using the calculator to solve this problem, if you know how to do this problem directly off the calculator, what you're using your calculator to compute is something called a binomial probability. Binomial probability. Right? It's a binomial probability because when you think about the prefix bi, what number comes to mind? The
2.
number 2. So that implies that there's only 2 outcomes. The 2 outcomes here is usually defined as P and Q. P being the success and Q being the complement of P, which we call the failure. Okay, so let me define all the variables for us, and I'll show you how to solve this problem by hand, where of course we're going to use the calculator, but just setting it up all by hand. So what we have is that, first of all, there's the variable n. N stands for the number of trials. Okay, the number of trials. X stands for the number of successes in n trials, or among n trials. P stands for the success rate of any one of the trials. And Q stands for the failure rate. It's the failure rate, which we can always compute by just taking 1 minus P. It's a complement, right? P and Q are mathematical opposites of one another. So you do, if you know P, you find Q by just taking 1 minus P. Another thing to note is that the n, oops, wrote this wrong. N choose X is is what we defined as a sorry about this. N choose X is what we define as the combination rule. So is defined as n factorial over x factorial times n minus x factorial. Okay, so that's everything that you need to know about this formula. Now, in this problem, there are some key phrases here that you need to know as well. Because depending on the wording of this problem, there's usually 5 cases. So I'm gonna slide this up just a bit here. Okay. There are basically 5 different scenarios. The first scenario is if we have exactly A. If we have exactly A, then this implies that X is equal to A. If we have less than A, then X is less than A. That's how you represent it mathematically. Less than or equal to A is the same thing as saying at most A. That's the one that we're going to use in this problem, since it says she gets at most 3 successful serves. So here we're going to look at most 3, or at most A for now is X is less than or equal to A. And then you have the greater than and at least. So greater than A means X is greater than A, at least A means X is greater or equal to the value of A. So let's define everything in this problem. Well, when I reread this problem, I'll have it above here. What is the value of N? How many trials do we have?
9.
We're going to have 9 trials. X is going to be, since it says at most 3, X is going to be less than or equal to 3. Now, since X is less than or equal to 3, then this would imply that X is equal to a few values here. What would be the first value that you can say X would be equal to?
3.
3. And anything below 3 comes after, right? So we can have 3. So what's the next number that's less than 3?
2 and 1.
2, then 1. But then there's another number that comes after 1. That number is going to be what?
0.
0. So that means that since X is less than or equal to 3, then X can equal to the one of the 4 following numbers, 3, 2, 1, and 0. So that implies that we have to use this formula, this binomial probability formula, 4 times. Now, P stands for your success rate. So what is my success rate?
51%.
51%. And what is 51% as a decimal?
0.51.
0.51. And Q is 1 minus P. So we take 1 minus 0.51, which is
0.49.
0.49. So on the top here, I defined all the variables for us. We have that N is going to equal to 9. X is equal to 3, 2, 1, and 0. P is going to be 0.51, and Q is going to be 0.49. All right, so if I want to compute the probability now that X is at most 3, or probability of getting at most 3 here, then this is the same thing as computing the probability of the 0 case, plus the probability of the 1 case, plus the probability of the that X is equal to 2, and the probability that X is equal to 3. Again, we're going to have to use the formula 4 times. So what I'll do is I'll set it up. We're going to do a couple of them just to show you how you do at least 2 of it. The other 2, I'll give you what those values are, and then we'll just add it all up at the end. Okay, so I'm just going to scroll down a bit. So I'm going to save some room here just to do some calculations. All right, so I'll split this in half, and I'll split this in half. Actually, I'll save a little bit more room. Since I said we'll do the other 2, I'll give you what the values of the other 2 are. Okay, so if I want to compute the probability of 0 by our formula, this is going to look like the following. N was 9, x is 0 here. So we're going to get 9 choose 0 times 0.51 raised to the 0 power times 0.49 raised to the 9th power. Why is it 9 here? It's 9 because it's n minus x. So if n is 9, x is 0, 9 minus 0 is 9. We have to compute p of 1. So this is going to be this is going to be 9 choose 1 times 0.51 raised to the 1st power times 0.49 raised to the power of 9 minus 1, which is 8. Then we do the probability of 2. So this will be 9 choose 2 times 0.51 to the 2nd power times 0.49 to the 7th power. And for 9 choose 3, this is going to be the probability of 3 is going to be 9 choose 3 times 0.51 raised to the 3rd power times 0.49 raised to the 6th power. Okay, so let me show you how you get the 9 choose 0 part. How to figure out that number. Well, 9 choose 0 is the same thing as saying 9 factorial over 0 factorial times 9 minus 0 factorial. Okay, so what is 9 minus 0? Well, that's 9. So this will give us 9 factorial over 0 factorial times 9 factorial. Now, do anybody know what 0 factorial is?
Doesn't it become 1?
That becomes 1. So if 0 factorial becomes 1, then that 0 factorial goes away because 1 times any number is just that number. So this will become 9 factorial divided by 9 factorial. Well, what is 9 factorial divided by 9 factorial?
1.
That's going to be 1, right? Anytime you divide the same number top and bottom, this is going to equal to 1. Okay? So that first number, 9 choose 0, is just going to be 1. Now, if you look at 0.51 raised to the 0 power, do anybody know what, if you have a base and you raise it to the 0 power, it's always going to be what?
1.
It's always going to be 1. So what we're really computing here is 1 times 1 times 0.49 to the 9th power. Well, the ones you don't really have to worry about because, again, any number times 1 will just give you back the original number. So if I work out 0.49 in my calculator, 0.49 raised to the 9th power, and let's just say I take the first 5 decimals that I see in the calculator, the first 5 decimals that you will see, right, after the decimal point, the first 5 decimal numbers will be 0.00032. Okay, so this first number, the probability that it's 0 will be 0.00032.
I get another result for that one.
What did you get, Edwin?
0.00162.
Maybe I did something wrong. Let's see.
It's 40.41 to the
0.49 raised to the power of 9.
Yeah.
Oh, you're right. I did that wrong. My bad. Oops. Thank you, Edwin. I fixed that. Okay. So that's the first one. Let's do the second one. If I want to do 9 choose 1, then by the condition by the condition rule, no, combination rule, by the combination, you get 9 factorial over 1 factorial times 9 minus 1 factorial. So I'll show you how to simplify this. Look at the denominator. What is 1 factorial? What is
0?
No. 1 factorial is the same thing as 0 factorial, so they're both 1s. Right? So just note 0 factorial is equal to 1, and 1 factorial is also equal to 1. Okay? So the 1 factorial goes away. Now, what's 9 minus 1? Well, that's 8. So we're going to have 9 factorial divided by 8 factorial. Now, by the definition of factorials, depending on the number that you start with, it's just going to be a product where you go down, you decrease this number, whatever the value is, by 1 until you get to 1. Now, the thing here is that 9 factorial is the same thing as 9 times 8 factorial, because what is 8 factorial? 8 factorial is going to be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 9 factorial, in short, is just 9 times 8 factorial. Now, because I have an 8 factorial on the bottom, then the 8 factorial that's on the top gets canceled with the 8 factorial that's on the bottom. So what number are we going to be left with? We're going to be left with 9. We're going to be left with 9. So what do I have here for probability of 1? Well, we're going to have to do 9 times 0.51 raised to the second power times 0.49 raised to the 7th power. Okay, so you can answer all of this into your calculator, but just be careful with the way you write it. So I could have did 9 times 0.51 squared times 0.49 raised to the 7th power? No, 8th power. Sorry, what did I wrote? I wrote this wrong. My bad. It should have been 0.51 to the first and 0.49 to the 8th. My bad. I was looking at the bottom left. So let me just redo the math. You get 9 times 0.51 times 0.49 being raised to the 8th power. So if I did this correctly, can somebody tell me what the first 5 decimal numbers will be.
How many decimals you said?
5 decimals.
Oh, 0.15253.
Well, there should be a number that came after the before the 1. Right? So I think you made a slight mistake, Edwin. I think it's going to be 0.01525.
Yeah.
Okay, you get 0.01525.
Yeah.
Professor,
Mm-hmm.
was this supposed to be a 7 or an 8 to the power of 0.49?
For the probability of 1 here is going to be power of 8.
Okay.
Yeah. I made a typo when I was writing out the solution here on screen. I was looking at the bottom left and I saw the 2 and the 7 and I wrote 2 and 7 by accident. Okay, you get 0.01525. And now you'd have had to repeat this for the probability of 2 and the probability of 3. What I'm going to do is I'm just going to show you quickly how you get the 9 choose 2 and the 9 choose 3. So for the 9 choose 2 part, you get 9 factorial over 2 factorial times 9 minus 2 factorial. All right, let's try to simplify this. Look at the bottom. The 2 factorial is just going to be, if you expand, if you just leave it alone for a moment, it's 2 factorial. But 9 minus 2 is 7, so you get 7 factorial. Now look at the bottom. Which factorial is bigger? 2 factorial or 7 factorial?
7.
7. So you can rewrite 9 factorial as 9 times 8 times 7 factorial, all divided by 2 times 1 times 7 factorial. Now the 7 factorials would cancel out, and what you're left with is 9 times 8, which is 72, divided by 2 times 1, which is 2. And if you work this out, 72 over 2 is 36. So this first number, 9 choose 2, is really 36. So you take 36 times 0.51 raised to the second power times 0.49 raised to the 7th power, and you get the first 5 decimal places. So 0.51 squared, 36 times 0.51 squared, you get an answer there, and then you multiply that by 0.49 raised to the 7th power. The first 5 decimals that you will see, can somebody tell me?
0.0635.
0.0635, and then technically after that 5 was a 0, so I'm just going to include it. So we get 0.06350. Okay, and for your last number, 9 choose 3, that's going to be 9 factorial over 3 factorial times 9 minus 3 factorial. So what is 9 minus 3? Well, that's 6. So you get 9 factorial over 3 factorial times 6 factorial. Now, which factorial is bigger, 3 or 6?
6.
6. So you can rewrite this as 9 times 8 times 7 times 6 factorial, all divided by 3 times 2 times 1, right? So I expand the smaller factorial, leave the bigger factorial alone, so that way I could cancel it out with the one that's on the top. So what are we left with? 9 times 8 times 7. That will give us 504. And then 3 times 2 times 1 is just 6. So what is 504 divided by 6?
$84.
You get 84. So for 9, choose 3. This is going to be 84 now, times 0.51 raised to the third power times 0.49 raised to the sixth power. So you do 84 times 0.51 to the third times 0.49 to the sixth power. If you do this correctly, what is the first 5 decimals that you see?
Point 15422.
0.15422. And you write that out here. Okay, and then you just add up those 5 decimal numbers, right? So 0.0016 plus 0.01525 plus 0.06350 plus 0.15422. This will give you 20.23313. So if the question asks you to round to, like, let's say 4 decimal places, so the answer would have just been approximately 0.2331. And that would have been now the solution. Oof, what a problem. Now, don't get me wrong, I did this problem by hand. Everything was done strictly by hand, except for just doing the the multiplication stuff. Yes, there's a way to put factorials into the calculator, and yes, there's a way to do this, solve this exact problem in the graphing calculator. But again, I don't know what technology everyone uses in their class. Like, I don't know if you use a what type of calculator you use, if you use a graphing one, if you use a scientific one, or if you use Excel. I don't know. We're all somewhat different with the technology stuff component. So I did everything by hand. Okay, so if you got the same answer using your technology or an approximative answer like 0.2332 or 0.2330, then that's fine. Okay. Is there anybody with a question that they would like to ask me? Okay. So again, that was problem number 5. We were dealing with the binomial probability. If you ever rewatch this video or you have the notes down, be mindful of the formula and the key phrases to look out for. Depending on the key phrase, it tells you how many times I would use the formula. Like, for example, let's just say if it was exactly A, right? If it was just exactly A or exactly 3, then how many times I would have used the formula?
8 times.
Say it again, Edwin.
8 times.
Not 8 times.
But
If you have the
usually
exactly case, you use the formula only once.
Oh.
But depending on the key phrases, again, it tells you or gives you a clue of how many times you have to use the formula. All right, so that's problem 5. Now we're up to problem number 6. So problem number 6 states that the overhead reach distances of adult females are normally distributed with a mean of 202.5 centimeters and a standard deviation of 8.3 centimeters. Find the probability for 25 randomly selected distances is greater than 200.3 centimeter. Okay, so first of all, what can we tell about the distribution here for problem 6? In other words, our data set from a visual point of view is going to look like what type of shape?
bell shape.
It's going to look like a bell shape. What gives it away that it's a bell shape?
Normally distributed.
That's right. It's normally distributed. Right? So normally distributed implies that we're looking at a bell shape. All right, so I'm going to draw my bell, and then we're going to work this problem out. All right, so let's say that's our bell. What do I know about the bell? Well, what's located at the center?
The mean.
The mean. The mean was 202.5. So we have 202.5. That is the mean for this data set. Now, another thing to note is that it has to give you a standard deviation. The symbol for the standard deviation is little sigma. It was 8.3. So the question now states, find the probability that the mean for 25 randomly selected distances is greater than 200.3. So because it says that we have to find the probability that the mean for 25 randomly selected distances is greater than 200.3, then this distribution that we're looking at is not in terms of x, but rather in terms of x bar, the sample mean. Okay, so we're looking at a distribution of the sample means where I know that n is equal to 25. And by the way, that's okay that n is 25. I'll explain why in a bit. And again, it has to be that the probability that the mean for these 25 selected distances is greater than 200.3. So on my graph, let's say somewhere around here is where 200.3 is located. Now, since I have to find the probability that it's greater than this value, what side of this bell-shaped curve am I going to shade in? Am I going to shade the left or the right?
Right.
We're going to shade in the right. So we're going to shade in this piece. So out of all 3 of the cases, when you're solving these type of problems, I'm dealing with strictly a right case. Again, it's a right case where we did involve a sample mean. So the way that we solve this problem is we transform our sample mean in terms of z. Do anybody knows the formula that I use to transform x bar in terms of z? Anybody know the formula?
X minus mean divided by the standard deviation.
Unfortunately, Malik, that wouldn't be the formula that I use here. You see, x minus the mean divided by the standard deviation. You use that to compute z. But more importantly, that's for when you deal with a individual value here. Are we dealing with an individual value? No, we're not. Instead, we're dealing with a sample mean, right? 200.3 is a sample mean. I'm going to call that value x bar 1. Okay, x bar 1. That's a sample mean. So because that's a sample mean, I cannot use the original z-score formula because I'm dealing with an individual value. Instead, I use a variation to this formula. It's a slightly different one. And what would be that formula?
Z equals X bar minus mean over the standard deviation divided by the square root of the sample.
That's right, divided by the square root of the sample size, which is n. So this is the correct formula that we use here when we're involving sample means. Sorry. So we can use this formula. It comes from the central limit theorem, provided that one of the two cases are satisfied, right? Either n is greater than 30, or 2, the original data is normally distributed. Now, I know that I'm using this formula for two reasons. One, I'm not finding the probability of a single value, but rather for a mean of values, namely when n was 25. Now, because n is 25, which is less than 30, then this first condition wasn't satisfied. However, the second condition was. The data was originally normal. So if the data is originally normal, then the distribution of the sample means is also going to be normal. Therefore, it would resemble this bell-shaped curve. Since it resembles the bell-shaped curve, the sample means, the distribution of it, can be standardized using the z-score formula. Okay? You can standardize it using the z-score formula. So let's find the value of z, and then I'll show you how to write it out, how to write this all out in words. Okay, so if I want to find z, I take the value of my x bar, subtract it from the population's mean, divided by the standard deviation, divided by the square root of n. So what is my x bar here? Well, x bar is 200.3. When I subtract this from the population mean, it's 202.5 there on top. The bottom is going to be 8.3, your standard deviation, divided by the square root of n, which is 25. Okay, so let's work this out. First, do this one step at a time. What is 200.3 minus 202.5?
Negative 2.2.
Negative 2.2. So you get negative 2.2 on the top. Now, on the bottom, do anybody know what's the square root of 25?
5.
5. So you take 8.3 divided by 5, and what would you get?
Point 1.66.
Here you go, you got it, 1.66. Sorry, I was cutting you off. My bad. So you get negative 2.2 divided by 1.66. When you're computing z values, think of it as money, right? Money always, currency-wise, it always rounds up to 2 decimal places, or you round it to 2 decimal places. So if I round z to 2 decimal places, what will I get?
Negative 1.33.
Yeah, negative 1.33. Oops, sorry. All right, almost done here. So I'm gonna write this out in words, and then we're gonna basically the process of what we just did, and I'll show you how to do the calculations, how to get the final answer. So when x1, your sample, x bar 1, your sample mean was 200.3. When you standardize it, the value of z becomes negative 1.33. This allows me now to use the z table, but I got to be careful. So originally, finding the probability, by the way, is the same thing as finding area underneath this curve. So the area to the right of z equals negative 1.33 is the same thing as the area to the right of our, sorry, my bad. I did this backwards. You first start with the original variable. Area to the right of x equals, or x bar equals 200.3 is equivalent to finding the area to the right of z equals negative 1.33. Now, anytime you deal with the right case and you're finding the area under the curve, does the z table give us the area to the right?
No.
No, the z table only give us the area in which direction?
To the left.
To the left. So the area to the right of z equals negative 1.33 is actually equal to 1 minus area to the left of z equals negative 1.33. Okay? So now I just got to find what the area to the left of this z value looks like on the z table, and then subtract it from 1. So the good thing is I pulled up, by the way, if you have Pearson MyLab, if you have your Pearson MyLab account, or if you have the stats book in LACX class, you can find your Z table there as well. But this is again something that I found on Pearson's MyLab for 132. So if I have to find z equals negative 1.33, I looked at my standard normal z table. There's the negative z scores and the positive z scores. So for the negative z, since z was negative, I look at the negative side. I begin with negative 1.3, and I know it ends with a 3. So I look at when that row and column intersects. So that row, oh, my bad, this is a little too big. This row intersects with this column will give me the area to the left. So what value do they intersect at? Can you guys see it?
0.0918.
There you go, 0.0918. So I'm going to go back, I'm going to write out this value and then subtract it from 1. All right, so what's 1 minus 0.0918? Whatever it is, that will be your answer.
91.
Give me the 4 decimals, Tim.
Okay.
0.9082.
9082. Okay. 0.9. No, it can't be 9. Is it 90? Yeah, it's 90. Wait.
Yeah, it's 90.
Yeah, 9082. Okay, and that's it. That would have been the solution. So I'm just gonna rotate the screen so that way you can see both the whole problem. So for problem 6, just gonna recap here. The overreach distance of the adult females, that variable is normally distributed. So that means that the shape that you should sketch, right? The image that you should draw is a bell. Draw a bell-shaped curve. It says that the mean of this bell-shaped curve is going to be 202.5 and a standard deviation of 8.3. Because it says find the probability that the mean for 25 randomly selected distance is greater than 200.3, just note that I use the second formula for z, where z is equal to x bar minus the mean divided by the standard deviation divided by the square root of n. If it's stated, find the probability that one of the distances is greater than 200.3, one distance or an individual distance is greater than 200.3, then I would have had to use the original or the first z-score formula. Now, because again, it's a greater than case, that implies a right case. So once I find the value of z, the area to the right of that z value is equivalent to saying 1 minus the area to the left of z. Use your z table to get that value, and then, of course, subtract it from 1. If the data set wasn't normally distributed, then n had to have been greater than 30. Okay, so if the problem said this time, excuse me, that the overhead reach distance of adult females had a mean of 202.5 and a standard deviation of 8.3, where it didn't use the word normally distributed, then the value of n had to be bigger than 30. So it says something like, find the probability that the mean for, let's say, 35 randomly selected distances is greater than 200.3, then the same formula can be used because n was greater than 30. If it didn't make any mention of normal and n was less than 30, then I couldn't use this formula. Any questions here to problem 6?
Can you repeat the part that you were saying about using the other formula?
Using what other formula?
C equals x minus n.
Yeah. So I would have only used z equals x minus mean divided by standard deviation if one distance or an individual distance is greater than 200.3.
Got it.
It has to be an individual distance or individual data value. Any other questions? All right, let's look at problem number 7 now. So number 7 states that a research institute poll asks respondents if they felt vulnerable to identify theft. In the poll, n is equal to 1068 and x is equal to 542, who said yes. Okay, so in a survey, in this poll, there were 1,068 respondents. 542 of them said yes. It says use a 95% confidence interval. So I got to construct a confidence. Use a 95% confidence level. So I have to construct a confidence interval here. We want to find the best point estimate of the population's proportion, identify the value of the margin of error, construct your confidence interval, and then part D states which of the following statements correctly interprets the confidence interval. So, let's look at part A. Find the best point estimate of the population's proportion. So, population proportion is denoted as P. Do anybody know what's the best point estimate of the population's proportion?
It should be x divided by n.
It is x divided by n, but what does the x divided by n stand for?
P hat.
P hat, and what does P hat stand for?
Best point estimate.
Yes, but in particular, what does that notation describe?
Probability of success.
No?
The sample proportion.
There you go, Edwin. It's a sample proportion. So for part A, the best point estimate of P, where P again stands for population's proportion, best point estimate of the population proportion is P hat, where we call that the sample proportion. So the way that you compute P hat is exactly how you describe it. P hat, oh my bad, not P bar, P hat, is equal to x over n. So the problem clearly identifies x and n for us. X is 542, n is 1068. So I'll take 542 divided by 1068 and round this value to 3 decimal places. And that would be part A solution. So 542 divided by 1068 will be what?
What do we round it to?
3 decimals.
0.507?
0.507. Okay, good. That's part A. Part A is done. Best point of estimate, 0.507. Part B states to identify the value of the margin of error. So if you want to compute the margin of error, we call that E. The margin of error is computed by the following formula. It's equal to the critical value, Z alpha over 2, times the square root of P hat times Q hat over N, right? P hat times Q hat divided by N. You would compute that and then take the square root of it. Now, to figure out Z alpha over 2, you can use your table, right? If you recall, in this problem, what is the confidence level here?
95%.
So we have 95% for a confidence level. So I'll call that C dot level. So I just abbreviated confident. You can find your critical value, Z alpha over 2, for the 95% confidence interval, right? For the 95% confidence level, find the critical value using the Z table. Okay, so I'll come right back to this. If you look at the Pearson's Z table, they leave these little footnotes on the bottom. Namely, if you look at the positive Z scores, you look to the bottom right, do you see where it says confidence levels?
Yeah.
If you're given, excuse me, give me 1 second. If you're given a 95% confidence level, then as a decimal number, that's 0.095. Well, if it's 0.095, then it gives you the critical value to use. Well, what is the critical value that it gives us? It's 1.96. So when I go back into our slides here, the Z alpha over 2, that's your critical value. That critical value here is going to be precisely 1.96. So the 95% confidence level, 90%, or even 99%, you can find any of those critical values using the Z table. It's on the positive side, of it, and you look at the bottom right. So Z alpha over 2 is 1.96. Now we're going to multiply this by the square root of p hat times q hat divided by n. So I know that p hat, by the way, is 0.507. If p hat is 0.507, do anybody know what's q hat going to be?
0.493.
That's right. See, p hat is going to be 0.507. So q hat has to be 0.493, right? It's 1 minus whatever the value of p hat was. Sheldon, that will be for tutoring. I won't be able to answer that one at the moment. So we get 0.493. Sorry, I'll make this a little bigger. And then you divide by the square root of n. The square root of n, or sorry, the value of n was 1068. Okay, so you can compute the square root first, right? Compute whatever's inside the square root, take the square root of that value, and then multiply it by 1.96. So to save us just a little bit of time, I'll give you this value. If you round e to 3 decimal places, it turns out to be 0.030. Okay, so we've got our solution to part A. That was the best point estimate. It was 0.507. And now we got the margin of error, which is going to be if you do this calculation correctly, when you round it to 3 decimals, it turns out to be 0.030. All right, now you go and do part C. So part C, you construct the confidence interval. The confidence interval is going to be p hat minus e is less than p hat greater than plus e.
I got another value for the margin of error.
What did you get?
0.0299.
Yes, but when you round, so I'll write it in the chat so everybody sees it. If you have 0.0299, then when you round it to 3 decimal places, the first 9 that's directly to the right of the 2 becomes a 0, and then you add 1 to the 2, right? So in other words, if you round 299, the next number has to be 300, right? So it'll be like
Got it. I see now. Thanks.
Mm-hmm. All right. So p hat is 0.507 minus 0.030. So you do 0.507 on the other side plus 0.030. If you work this out, you get the confidence interval that will tell us that we can be 95% confident that the interval from this region contains the true value of the population's proportion. So 0.507 minus 0.030 is 0.477 less than p less than 0.507 plus 0.030 is 0.537. That's your confidence interval. So if you have to write a statement regarding so that we did part C there. Part D was to say write which of the following statements correctly interprets a confidence interval. The ones that we could eliminate automatically are the ones that does not use the word confidence. Right? So for example, you can get rid of the one that says 95% chance. You can get rid of the one that says 95% of the sample proportions. So you're just left with two options. Now, the first option says one has a 95% confident that the sample proportion is equal to the population proportion. That's not true. That's not true here. Our sample proportion 0.507 is not equal to the population's proportion, but rather, so I'll cross that one out as well. The only correct option here is the last one. So one has a 95% confident that the interval from the lower bound, that lower bound being 0.477, to the upper bound, which was 0.537, actually does contain the true value of the population's proportion. All right, any questions to problem 7?
Professor, can you scroll down a little?
Sure.
Thank you.
I was still trying to fit the answer choice to part D there. The one that's on the top. The one that I put the check mark on. I was trying to keep it on the screen. Only thing to be careful with in this problem, the only tricky part is the margin of error, okay? Again, if you have the z-table, you can find that critical value using the z-table. The common ones that are mostly used are 90, 95, and 99. So I don't think you will see 96, you won't see 94, you won't see 80, you won't see 85. You should mostly see 90, 95, or 99. When you compute the square root of that number, I recommend that you do that first, then multiply by the 1.96 at the end, or whatever your critical value was, and then round the margin of error to 3 decimal places. Once you have your best point estimate, your margin of error, the confidence interval is not that difficult to construct, because you either you're on one side you're subtracting those two values, and then the other side you're adding them. All right. Any other questions? We got one more to go, but any questions? All right, let's get this last problem out of the way, and that would wrap up our review today. So we got problem 8. Problem 8 is a problem involving hypotheses testing. So we're gonna look at one example of it today. On Tuesday at 6 p.m., we'll look at a second example of it. Okay, so it says, consider a drug used to help prevent blood clots in certain patients. In clinical trials among 5,750 patients treated with this drug, 153 of them developed the adverse reaction of nausea. Use a 0.10 significance level to test the claim that less than 3% of users develop nausea. And if you read parts A through D, the most important thing here is that you need to recognize that you're using the p-value method. Right, you're going to identify the p-value for this hypothesis test. And then, well, because we're using the p-value method, there's certain steps. Okay, so for each part, parts A through D, I'm going to answer this using 6 steps. So part A will have 2 steps for us. Part B is going to have just 1 step. Part C is going to have 1 step, and then part D is going to have 2 steps. So here's part A. For part A, based on the way that this problem is worded, we have to do 2 things. We have to do step 1, which is solving part A, stating the null and alternate hypothesis. And then step 2 is a little quick sketch. Okay, so step 2 is the sketch. Step 1 is to state your null hypothesis, which we denote as HO, and we're going to state the alternate. So what would be my null hypothesis here?
P equals 0.03.
That's right. P is equal to 3%, which as a decimal is 0.03. So that's the null. That's the one that we assume is true. We're assuming that the population proportion is equal to 3%. The alternate hypothesis, HA, is going to be what?
P less than 0.03.
P is less than 0.03, right? So we state the null and the alternate hypothesis, but between these two hypotheses here, which one is the original claim? Is it that P is equal to 0.03 or P is less than 0.03? What is the claim?
P is less than 0.03?
Yeah, it says test the claim that less than 3% of users develop nausea. So HA is our claim. Okay, HO is something that we universally is accepting as true, but the alternate hypothesis says no, P is less than 0.03. All right, so let's make a sketch of our situation here. If you want to make the sketch, you use the, well, first of all, since the alternate hypothesis says that P is less than 0.03, what type of test do we have here? Is it going to be a left tail, right tail, or a two-tail test?
Left.
It's a left tail. We're going to have a left tail test. The inequality symbol, or the symbol in your alternate hypothesis tells you what test it is. So less than is left tail. Just aside here, the greater than symbol is a right tail, and the not equal is a two-tail test. But again, because we have the less than symbol, it's a left tail. Okay, so here's our sketch. again, we're gonna have to use our significance level. We call that alpha. So alpha equals 0.10. This is now going to be the area in the left tail. So I'm drawing a normal distribution. Here's my bell. But now the area in that left tail, say here, here's my left tail. The area is alpha. Okay, so that's step 1 and 2 done, right? Part A, you can state your null, you state your alternate. Step 2, it doesn't say it on the exam, but it's good to have a visual. There's the visual, because we'll use it when we get up to part D. All right, so now we move on to part B now. Part B. So part B states that we have to compute the test statistic for this proportion. So what is the test statistic that we're going to compute? Is it going to be done using a z-test, a t-test? What type of test will I use here?
Z-test.
It's a z-test. So the test statistic is z. I abbreviate the z as z-test, right? So instead of saying test statistic, I call it z-test. And the formula for it is equal to p hat, the sample proportion, minus the population proportion, which we assume is true, that's bad, divided by the square root of p times q over n. Okay, so I'll show you how to compute this one step at a time. P hat, again, is the sample proportion, and we saw back in problem 7 how to compute it. You take x over n. So if you reread this problem, what is the value of x?
$153.
153, and the value of n has to be 5,750. So we get 153 over 5,750. If we round this to, let's just say I round this value up to, well, yeah, let's say I round this to 5 decimal places, or I just take the first 5 decimals. I think what you'll see is 0.02660, right? So the more decimals you use here, the better, because again, we're doing this by hand. So we're not going to get a precise answer. We're going to get an estimated answer. So the more decimals you use, the better.
Wouldn't it be 0.02661?
What came after the 0?
8.
An 8? Okay, so let's make that a 1. No biggie. So yes, that will be your sample statistic. I know that p was equal to 0.03. So now I take the difference between these two values, right? If I do p hat minus p, this is going to be 0.02661 minus 0.03. So what do I get here? When I do the subtraction, let me know what you got.
Are we still rounding to 5?
No, if you yeah, keep it at 5 decimals for now.
So I got negative 0.00339.
Yeah, we'll keep that. Don't worry. Negative 0.00339. Okay, so that will be p hat minus p. That's the number on the top. Now he's got to figure out what's the number on the bottom. So the way that we get that number on the bottom is, well, okay, I know p is 0.03. Do anybody have any idea what the value of q is going to be? If P is 0.03, what should be the value of Q?
1 minus 0.03.
1 minus 0.03, which is
0.97.
0.97. And the value of n, I know, is 5,750. So I have to compute the square root of 0.03 times 0.97 divided by 5,750. If we, again, round this to 5 decimal places, what will we get? I think it's 0.00224, but let me just double check. Or 0.0025. So the more decimals you use, it's the better your approximation is going to be here. So if I take negative 0.00339, divide that by 0.00225, we should get something, if I round this to, again, 2 decimal places, let me know what you get. So by the way, this was step 3, computing the value of z. Does anyone have a value of z here for me? When you round it to 2 decimal places?
I got negative 1.51.
That's right, negative 1.51. So that's our z-test. Okay. Now what we're going to do in part C is compute. Yeah, go ahead, Edwin.
So on class, we normally stop at 6 decimals. So is that fine if we stop at 5?
5 or 6 is reasonable.
Okay.
The more, like I said, Edwin, the more decimals you use is the better. Better the approximation.
Got it.
So maybe if you use 6, it'd have been like negative 1.51 or negative 1.52.
Got it.
Mm-hmm. Okay, so now you go on to part C. Part C states is going to be step 4. And that is where you have to compute the p-value. You see, when you want to compute the p-value is going to be precisely the area in the direction of the null of the alternate hypothesis, right? Is the area of the z-test that we just computed in the direction of the alternate hypothesis. So look at our sketch here. If you look at our sketch, again, what type of case will I have here? Will it be a left, right, or between case? It's a left case. So if you want to compute the z-value in step 4, your p-value, based off of the visual, is going to be equal to the area to the left of the test statistic. Our test statistic here is z-test equals negative 1.51. Now, if I want to find the area to the left of our test statistic, just look at the z-table. So if I go back, I'm going to come right back to this tape, come back to this. If you look at your z-table, now I look at the negative side. We're locating negative 1.51. So here's negative 1.5. it ends with a 0.01, so that row and column meets at 0.0655. Okay, so when you use the z-table, the area you get to the left of negative of the z-value, the area to the left of z equals negative 1.51 is 0.0655. So I go back to my sample final, go back to the slides, we get 0.0655. All right, now that we've done part C, we do part D. Part D is a two-step process. It's step 5 being the decision that we make, and step 6 is to write out your conclusion. The conclusion is typically written in just plain English. So the way that we make our decision is we compare the p-value that I just computed to our significance level. So the p-value was equal to 0.0655. Alpha, the level of significance, was 0.10. So you're comparing the p-value to alpha. Is the p-value greater than or less than alpha?
Less than.
It's less than. So if the p-value is less than alpha, do we reject or fail to reject the null?
Reject.
We reject the null hypothesis. So because we're rejecting the null hypothesis, we are accepting the alternate, and the alternate was our claim. So we write out our conclusion based on the claim. We say, in step 6, there is enough or sufficient evidence to support the claim that less than 3% of users develop nausea. And that would have been it. So I'm just going to rotate this back, so that way you can see parts A through D. The only issue is I can't really zoom in on this, because if I do zoom in on any parts, maybe this is as much I could do, then some parts will get omitted.
I have a question.
Go ahead.
So if the p-value is greater than alpha, then you fail to reject?
Then you fail to reject the null.
And that means there's not enough evidence, right, to support the claim?
That's right. That's right. If you fail to reject the null, then there is not enough evidence to support the claim that less than 3% of users develop nausea. That's gonna be a tough one, Sheldon. You'll probably have to come see me at the center for it.
For part B, for part A, what's the final answer? That's good. I didn't even say sweet.
Oh, the final answer was just stating the null and the alternate hypothesis. The recording will be definitely located on our website, and of course it'll be on YouTube. So if you guys want, let me just go to YouTube real quick. Do you guys have a Gmail account?
Yeah.
If you have a Gmail account, you can just subscribe to our YouTube account, and once you're logged in, right? So I'm sending the YouTube account here. Once you subscribe to the YouTube account, the YouTube page, you usually get a notification when we upload things. Anybody else with a question? Oh, you're welcome. You guys are welcome. Again, this Tuesday I'm gonna do a second review. So I'm gonna do something similar for the second review. But I'll show you like different ways this could be worded. Mohammed, that's a good question. Raphael, when do you think it's gonna be uploaded?
In about 3 hours, if YouTube is helpful enough.
Okay. Yeah, in like roughly 3 to 4 hours. What I think I have to do, by the way, Raphael, is I have to wait, let me end the Zoom. Sorry, let me just stop the recording.